Okay, so now I want to talk about the Marcus-Spielman-Srivastava idea. So what's the underlying idea of their construction, or actually proof of existence of Ramanujan graphs? And I'm going to be it's going to be extremely high level, but I'm going to kind of try and use and kind of motivate or tell you what are the questions that we care about in free probability through their idea. So free probability is much broader than just expanders. It actually has nothing to do with expanders as is. But through this, I hope that you'll be able to kind of figure out that there are some interesting questions that you need to solve in order to get this idea to work. And free probability will allow you to solve these questions. Okay, so what's the MSS idea? Well, you can say I want to construct a D-regular graph. One way of doing that is to consider the union of D matchings. It's actually a union that respects multiplicity. So if an edge appears twice, you encode the fact that it's appeared twice. But never mind. So here, for example, we have a union, a union of three, perfect matchings on 10 vertices. So that will give you a free regular graph. In terms of adjacency matrices, it means that you can write the adjacency matrix of a graph, a D-regular graph, as the sum of three matchings. And let me not write it as a matching plus another matching plus a third matching like that. Let me fix a matching, maybe some fixed matching that you want. Maybe you will fix vertex 1 to vertex 2 if you call the neighbors, the vertices by those names, and 3 to 4 and so forth. So that's M. Right, it will look like 1 0 0 0 and then 1 1 0 0 and so forth. And any perfect matching can be obtained using this matching by permuting the vertices names, right? So think of P1 as a permutation matrix here. And if you think about it, transpose conjugating the fixed matching with P1 will give you the matching that corresponds to the permutation, right? So now you have a matching between pi 1 and pi 2 rather than 1 and 2 if pi is the permutation that is encoded in P1. Okay, adding these three matrices will give you an adjacency matrix of a free regular graph in this case. And okay, now it's just a question of choosing the PIs, right? So well, not every D-regular graph actually can be written as the union of the perfect matchings. I encourage you to figure out why, but never mind that. These are some of the D-regular graphs, and a D-regular graph which can be written as the union of the perfect matching can be written like that. I mean, the adjacency matrix can be written like that. Right. But of course, now the question is how to choose the PIs. That was the question from the beginning. I mean, are there PIs for which this is Ramanujan and so forth? So the problem here is the sum, right? I mean, you have this matrix that you completely understand. By the way, its eigenvalues are either 1 or -1. It's a matching. Also this one, but the sum of these two matrices is, let alone the third one also, is, how does the sum affect the spectrum of, I mean, how does the spectrum of the individual matrices joins together when you sum up the two matrices, right? So let's consider that specific question now. If you are given two matrices, or let's consider graphs, two undirected graphs G and H, whose adjacency matrices are AG and AH. What can you say about the spectrum of the union of G and H, or more precisely, the spectrum of the sum of the adjacency matrices? So the point is, I mean, you of course you can do it. You can take AG and AH, add them together, and look at the spectrum. The thing is that you'll have to look at the eigenvectors, right? Because knowing the spectrum of AG and AH, doesn't constitute enough information to determine the spectrum of AG plus AH. right? For example, they could have the same eigenvector structure, and then the eigenvalues just add up. Accordingly, for every psi I, you take lambda I plus mu I or whatever. But if AG has a different set of eigenvectors than AH, then the eigenvectors matter. You don't know what the spectrum is not a function of the spectrums. But in a spectral graph, you really kind of want to insist of working with the spectrum rather than with the eigenvectors. It's just usually easier. It's enough information, but not too much in a sense. So if you insist of doing that, then a good idea is to try and rotate AH compared to AG. Right? So what do I mean by rotate? And then also, I should say also reflect maybe. I mean that, the eigenvector structure, as we said, affect the answer, like the spectrum of AG plus AH depend on the eigenvector structures. So if I'm going to kind of rotate or do something with the eigenvector structure of AH, maybe it will decorrelate the eigenvector structures, the eigenvector structure of the two graphs or the two matrices, and then I can hope that the spectrum of the individual graphs constitute enough information so to figure out what's the spectrum of the sum. Right, so that's the idea here. Just use a random enough Q to decorrelate the eigenvector structures of AG and AH. Now, the extreme is to take Q to be completely random in a sense. So what do I mean completely random? So it turns out that the right thing is to choose in a sense, a random, uniformly unitary matrix. Okay. So the right thing to do, the right name for that is to take the right measure over the group of unitary matrices called the Haar measure in this setting. So there is a way of actually decorrelating the eigenvectors completely. The problem is that it's not a graph anymore, right? So when you take this thing, which is the adjacency matrix of a regular graph, and you do a crazy thing to it, you transpose conjugated by a random unitary matrix, even a unitary matrix, usually you're not going to get a graph anymore. I mean, you're going to get a matrix. It's going to have essentially all entries non-zero, like with probability 1. And there could be negatives, there will be negatives there, and so forth. So it's very random, but it goes outside of the framework that we want. We want to work with graphs, right? So the other idea is to take a random permutation. So if you take Q to be a random permutation, you do get a graph because you permute the vertices. That's actually how we started the discussion, taking the sum of perfect matchings, permuted accordingly. But is it random enough, right? So what we learn towards the end of the course is that actually it is random enough. We'll see that there is a relation, essentially an equality, between what happens when you take a Haar random measure and transpose conjugate like that, and whether you take a permutation, a random permutation. It's called the MSS quadrature result, and quadrature is just a name for writing an integral as a finite sum. And if you think about it, here you have, if you think of expectations, here you have an integral, and here you just have a sum of all possible permutations. It's essentially a de-randomization result from the theoretical computer science perspective. Even though usually your de-randomized set is not n factorial in size. It's better than like Aleph. Okay, so what do I mean? Let me be a bit more precise about what I mean by quadrature result, or what is the relation between transpose conjugating with Haar or permutation? Well, it turns out that up to a slight lie, which is just technical and not interesting, so don't worry about that. So if you look at let's look at the right-hand side. So if you look at the right-hand side, and particularly at this polynomial, so the notation here is 3x. 3x is the characteristic polynomial of the matrix. So that's a characteristic polynomial of AG plus, you take the permutation, the corresponding permutation of the vertices of H and add them up. Right, that's a way of encoding the spectrum of this matrix, the characteristic polynomial. The spectrum is just the roots of that polynomial. And then you can ask, okay, I want to talk about like random permutations, initially at least. Then one way of doing that is looking at this expectation. Right, so what happens here is that you take a random permutation from Sn, and then you average the characteristic polynomials with respect to that measure. That's weird, I should say, because the information that you care about in each polynomial, lies in the roots of the polynomial. But the expectation that you take is in coefficient space, right? You just average the polynomials. So I mean, like if one polynomial is this and another polynomial is that, then their average is, this. So the average is with respect to the coefficients, not with respect to the roots. And it's completely unclear. I mean, you care about the roots. It's unclear what happens when you take the expectation in coefficient space, what happens to the roots. Okay, but that's that. And it's also unclear what is this polynomial altogether. I mean, forget about what it tells you about the root. To start with, it doesn't even seem like to be a real rooted polynomial, right? Because the fact that this is real rooted, all of these are real rooted, doesn't mean that their sum or average is real rooted. You can look at examples where you have like two parabolas like that. Anyhow, so it's not clear what this thing on the right is, but it is something that relates to what we are trying to understand. And we can bypass all this problem if we can be sure that there exists a permutation, a single permutation, whose say largest root, or maybe second largest root, lambda 2, smallest largest root, but let's say largest root is bounded by the largest root of this polynomial. Right? If we can show that there is a P such that the corresponding characteristic polynomial for that P has all its root bounded by the bound that we will have on the roots of the expected characteristic polynomial with respect to permutations that we are looking at, then this is something you want to understand, right? Because then you can argue about a particular permutation, namely about a particular graph. The point is that it's true. These characteristic polynomials that you have here form what's called an interlacing family of polynomials. They are structured enough so that, first of all, the expectation is indeed real rooted. So there is a sense of talking about the largest root and so forth. And secondly, indeed, there is a permutation, a particular one for which, say, lambda 2 of AG plus P transpose AHP for that P is at most the bound that you get on the second largest root of the expected characteristic polynomial. I can't say eigenvalue because it's not the expected characteristic polynomial is not the characteristic polynomial of a graph. Okay? So that's called the interlacing part of MSS, and we'll see it also towards the end of the course. Okay, and the equality that you have here is the quadrature part. It tells you that if you want to understand this polynomial, and as I said, you do want to understand it, because then using interlacing, you can understand something about a particular permutation, then it's enough to understand this polynomial. Now, this polynomial looks maybe harder to understand because this expectation is actually an integral, right? I mean, we're afraid of integrals as theoretical computer scientists, but actually it's easier to understand the left-hand side. It's not easy, but it's easier, and that's essentially free probability. That's the tools that will be available for us, but not quite. I mean, you will need another part of the MSS Fiore papers that tells you that. So you need a finite analog, I would say, of free probability, which will allow you to do so, because the operators here are all finite dimensional. But anyhow, let's not worry about that. So the takeoff from this part is that we really do want to understand this polynomial because it's related to this polynomial and that polynomial via quadrature. And that polynomial is good enough for us to argue using interlacing that there exists a P for which we know about the lambda 2 of the corresponding graph. Okay, I hope this was clear. So now the question remains. So, okay, now we are willing to look at A plus Q transpose PQ, an expectation, and when Q is sampled according to the Haar measure, but don't worry about that. So can you actually deduce something about the spectrum of the spectrum of this? So the spectrum of A plus Q transpose BQ, but namely, can you say something about the expected characteristic polynomial of this with respect to the Haar measure by the individual polynomials, like the one corresponding to A and B? Right? This essentially encodes the spectrum of A, that one encodes the spectrum of B. So can you understand the spectrum of this polynomial given those? And luckily and happily enough, this is indeed true. And it turns out that there is a formula for computing the spectrum of the sum of from the individual spectrums, and it goes through what's called the additive free convolution, which we will learn about. Okay, and again, that's a finite manifestation of free probability. There you have your measures are not on finite sets, so you don't have the characteristic polynomial representing them. You have something else, but it's essentially the same thing. It's not quite, but essentially the same phenomenon. Okay, so Haar is nice because you have these formulas that you can work out and literally compute spectrums of graphs that are sum of other graphs. But okay, so to give you a taste of how this works, I mean, I'm telling you here, so what happened here really is that I told you that A and B were kind of decorrelated, right? Because using that Q, and also putting the expectation here, but using the Q and taking an average Q, we kind of decorrelated A and B, right? So, and that's one way of doing that, kind of rotating B according to A so that we can again kind of decorrelate or free A and B from one another. And once we did that, we were able to actually deduce the spectrum of A plus B again from the individual spectrums. So let's take these questions more abstractly. Let's say you have two random variables A and B. Think of them as you can think of them as the matrices A and Q, B, Q transpose or something, not B itself, because B itself is not free from A. It's only an expectation when you rotate B, it is in a sense free from A. But let's not worry about that. Say you have these two A and B and they are free from one another, okay? So, and we wanted to understand something about, for example, the sum, right? So you want to understand the spectrum of the sum, namely the distribution of the eigenvalues of the sum. So if you want to understand distribution, you kind of really want to understand different moments, right? So you care about the expectation of this thing for every n. That will sometimes determine the measure itself, the density function. In normal cases, it will. It's enough to consider the moments to understand the distribution, usually. And so you care about things like when you open this up, and remember the things are non-commutative here. I mean, when A and B are matrices, it's non-commutative. You get this sum of all possible expectations of words of this form, right? So you really want to understand kind of the joint moments from the individual moments, right? So to understand this, you at the end of the day will need to understand those things, and that's the expectation of so that's the joint moment of A and B according to this choice A, B, B, A, and so forth. And what I'm telling you is that you can do that using, if A and B are free enough, you can do that by knowing only the individual moments, namely things like the expectation of A squared, and A to the K in general, and the expectation of all powers of B. Right, and the question is, if I'm telling you that you can do that, then what's the prescription, right? How can you do that? For example, in like the normal setting, commutative setting, in usual probability, if you have the expectation, for example, of AB, which is what we're looking at here, then because of its commutative, you can do this thing. You can commute A to the left side of B, and then using the definition of independence, you get this thing, right? So really, if you think about it, independence is a prescription or a rule for computing joint moments from individual moments, right? From the marginal moments. And the rule is, in the usual commutative setting, take the word that you care about, count how many A's and how many B's you have. Maybe you have KA's and LB's, and then the answer is the kth moment of A times the lth moment of B, right? And I'm telling you that in the non-commutative setting that we are talking about, there is a rule for doing that as well. So it must be another rule. So really, when I'm saying that and again, I'm completely vague here. We are going to be formal about it. It's just an introductory part of the course. Okay. So when I'm saying that A and B are free from one another, what I really mean is that it's not just something about the sum. I really mean that there is a rule for computing the joint moments of A and B from the individual moments. So what's the rule? And how does it doesn't conflict with the usual rule that we have and so forth? So let me tell you what the rule is for particular cases first. So it turns out that the rule actually agrees with the usual rule for short moments. Like if you take the expectation of A times B, then it's going to be us in the commutative case, the expectation of A times the expectation of B. But if you look at the expectation of ABA, ABA, then it's, even though A and B do not commute, it's still the case that it's the expectation of A squared times the expectation of B. However, and this is, I think, is the smallest example, if you look at the expectation of AB, then, in the usual world of when commutative random variables, that's the answer, right? But in the new world that we're going into, the answer is actually what's written here. So you have the expectation of A squared times the expectation of B squared plus the symmetric version for B. And then you subtract the squares of expectations of the individual variables. So actually, the fourth thing that may come to mind, which is what happens in the commutative case, doesn't even appear in this rule here, in that particular case. So you can ask, what are these rules? How did we come up to those rules? How are they useful and so forth? It brings us to the following question. So first of all, how do we define freeness? Namely, I was telling you that freeness is a situation that appears between random variables, such that when it appears, when it holds, it's like when they're sufficiently independent in a sense, then there is a way and freeness is the way. It's okay. It gives you the way. It's actually defined by the way in which you can compute the mixed moments from the individual moments. And you can ask, okay, is this like unique? I mean, we have the usual way of deducing the mixed moments from the individual moments. And now I'm telling you that there is another way of doing that. Is it unique? I mean, are there only these two, or there are others? Well, technically there is one more, but it's non-interesting. So yes, it is unique. So this is the probability that you didn't learn about. So there is one probability you learned about, and there's another one which you didn't, and it's this one in that sense. So in what sense it's unique? I mean, there is a set of axioms. We'll do that during the course. There is a set of axioms that if you are willing to take as granted, then you will see that you either get the usual probability or free probability. Okay, it's quite deep. Okay, so you can ask, okay, so why am I only hearing about it right now? I mean, I'm doing probability for quite some time, I guess. So why didn't I saw it so far? So it turns out that they live in different worlds. So free probability, so the rule that you have for computing mixed moments from individual moments, first of all, it's a non-commutative in nature. So when random variables commute, they can be free from one another. We'll formalize that. And secondly, it's an infinite dimensional phenomena. So matrices, for example, finite matrices, they're non-commutative, but they cannot be free from one another. So it's an infinite dimensional phenomena and non-commutative. So, as a theoretical computer scientist, you probably haven't encountered both, and probably none of those individually also. It also shed light, it also may make you worry. I mean, if it's a infinite dimensional thing, how can we use free probability to understand graphs, which are finite dimensional operators? Well, you technically can't. So what MSS did was to take some of the results of free probability and prove analog of them using actually different methods to the finite setting. That's why I'm referring to that as finite free probability. There are other ways you can probably, maybe people have done it, like try to draw from free probability results about finite free probability, but we're not going in that direction. I'm not sure what's known about that anyhow. Okay, but that might explain why you haven't seen free probability before. You can ask, is the formula useful? I told you there is a formula for computing mixed moments from individual moments. Well, yes, it is useful. You can actually analyze things with it. The issue is that, I mean, the formula is, as you will see, is extremely combinatorial. There is a combinatorial explanation as to which moments you have to take, like why did I took this and that, and why this is a minus and this is a plus, and generally it could be anything. So you can work out, so there is a combinatorics underlying free probability, but if you really want to work, try to understand, the spectrum of the sum. I mean, the sum, as we saw, the spectrum of the sum is a sum of many mixed moments. So if you want to understand that, you have to be kind of more wholesome. You can't look at any individual moment by itself and add them up. So what you do is you use analytic machinery. That's why we need complex analysis in the course, and I'll teach you what you need. It's quite elementary. It will take an hour or so. Other question you should ask, maybe just to close the discussion, is does indeed conjugating with HAR frees A from B? And the answer is yes, we'll see that. And of course, we still have to understand, after we understood free probability, how does quadrature and interlacing work, right? Right, so this leads me to the plan of the course, for the course. So let me tell you what we are going to do. So in this lecture, but in the next unit, we are going to start talking about non-commutative probability spaces. So that would be a non-commutative So a non-commutative probability. So we are going to start talking about non-commutative probability spaces. That's going to be very algebraic. We are literally going to look at algebras and so forth. No matrices, no anything. We are going to abstract things. That's always a good idea. So non-commutative probability spaces will be the gameplay. That's where we play. That's the stage of the play. Then I want to do a case study, like show you an example of understanding fairly simple but non-commutative random variables, a play, and that will enable us to introduce the key players like the semicircle element. The semicircle element is essentially the Gaussian free probability. That's the limit behavior of independent things. You will see, we'll learn about the Cauchy transform, which is the analytic tool that will enable us to compute, work with, say, sum of free random variables and so forth. And we'll learn about the Stieltjes inversion formula, which is a tool that enables you to go from moments to distributions. Because our non-commutative probability spaces are going to be kind of moment-oriented. We are going to think of random variables and encode information about those only based on the moments. And we will need an analytic way to move from the moments back to measures, if you want. So to do that, I'll have to talk about, even before the case study, I'll have to talk about a measure theory a little bit. I mean, we can not do that, but then there will be a gap in your understanding. And if you start at the wrong place trying to fill the gap, it could be scary. So I'm just going to give you a crash course on measure theory, just a couple, maybe 2 hours. And we will also need a little bit of complex analysis. We are going to use analytic continuation, which is weird if you don't know it. So I don't want to assume that you know it, because, as I said, this is a course for theoretical computer scientists. Usually you don't know what that is. Okay. So after that, we are going to finally see free independence, like the definition of when random variables are free. And we are going to prove a central limit theorem for free independence. Actually, we are going to prove the central limit theorem both for the usual classical independence and free independence. And you will see that at some point they diverge, but for quite sometimes they don't. And at the point in which they diverge there is something combinatorial that happens. In the classical setting, you look at all partitions of some set, and in the free case, you look at only on those non-crossing partitions. I think we'll talk about non-crossing pairings there, but never mind. So you seeing the central limit theorem on top of being like a thing you want to learn about when you look about new probability that someone tell you exists, will enable us to appreciate the difference between classical probability and free probability from the combinatorial perspective. Okay, and that will lead us to that's going to be actually a bit long. That's going to lead us to a discussion about the combinatorics of non-crossing partitions. This is going to be, as I said, the underlying combinatorial structure that distinguish free probability from usual probability. And once we did that, we'll be able to talk about free additive convolution, which will enable us to deduce the spectrum of a sum of free random variables from the individual spectrums and so forth. Okay, so that should take 9 weeks, hopefully. And in the last 3 weeks, we are going to kind of stop talking about free probability and redo what we need, like build up finite free probability. So it's not like we are going to use things we saw in free probability as is. We are going to use definitely some of the definitions, but we are not going to use the proofs per se, okay? Because freeness doesn't really exist in finite settings. But there are phenomena that hold in finite setting, which you probably wouldn't guess unless you knew free probability. I don't know, but once you know free probability, you can at least start guessing that might be the case and start proving it without the notion of freeness. It's something that you have in mind, but it's not something you use. And then after that, we'll see some applications. Definitely, we're going to see the proof of existence of Ramanujan graphs, bipartite Ramanujan graphs of every degree by MSS. Hopefully, we'll see other applications as well, but we'll see. Okay, so I think that's it for that unit. In the next unit, we are going to talk about, you're going to start being technical and going to talk about non-commutative probability spaces, and I'm going to slow down my pace, of course. Okay.